Okay, so this is part two, and we're going to talk a little bit about electric current, which comes from the flow of charge. And just like we've talked about heat flowing from hot to cold, like the second law of thermodynamics, in the same way, charge flows from the higher potential end of a conductor to the lower end, or to lower charge. And that potential difference means charge flow. And that flow is going to continue until both ends reach a common potential. And we'll have to talk about resistance too, because we don't want that flow to be quickly done and then we have no power, but we do want it to go slowly. So we'll talk about resistance too here. Okay, so if we had one end of a wire connected to the ground and the other with a Van de Graaff generator, for instance, we'd have this high potential energy that could be flowing. And there would be this brief flow and common potential would be reached. So to get a sustained charge flow, we need to maintain a charge difference. So what we're going to do, and we can talk about that a little bit too, but basically our focus here is how do these electrons flow. And in solids, of course, they carry the charge. That proton is bound in the nucleus. In liquids, the positive and negative ions provide the charge flow. We're going to measure electric current in amps, and the flow of 1 coulomb of charge per second is what an amp is. And as a secondary, we've maybe talked about that previously, is that a coulomb is 6.25 times 10 to the 18th electrons. In a wire that carries a current of 5 amps, basically what they're saying there is that 5 coulombs of charge pass any cross-sectional area of the wire per second. And to look at that, we do current, we symbolize that with I. That's going to equal coulombs of charge, Q, over time S. And the SI unit for amps, or for current, is amps. So a couple of examples here. Let's say I have 1.67 coulombs of charge passing through a filament light bulb in 2 seconds. What's the current? So we'll take 1.67 coulombs of charge, Q, over 2 seconds. We would get 0.835 amps. We could also ask, we'll do this question here, how many electrons pass through a filament in a bulb in 3 seconds if the current is 0.935 amps? So, yeah,
I forgot.
recording.
I didn't leave that.
Oh, okay, thank you. All right, so what we're going to do is take that 0.935 amps, and we're going to call that coulombs per second, because that's what an amp is, and we're going to say 3 seconds. And so the seconds will cancel. We'll get 2.805 coulombs of charge. And like I said in the previous problem, 1 coulomb of charge is 6.25 times 10 to the 18th electrons. And so we get 1.75 times 10 to the 19th electrons. Okay, voltage sources, we must have a potential difference to have that flow, and that sustained flow must have a pump to provide something, battery or something else like that, to provide that continual potential difference. So dry cells, wet cells, generators are capable of maintaining a steady flow. The electromotive force is just another name for potential difference. And in a home in North America, 2 holes and outlet provide a potential difference of 120 volts. So again, what that means is that 120 joules is supplied to each coulomb of charge that is flowing in the circuit. The other thing we should talk about is, oh, by the way, now you can do problems on current. The next thing we want to talk about is electrical resistance, and that's the amount of current that flows in a circuit. It's going to depend on the voltage provided by the source. It also depends on the resistance the conductor offers, the electrical resistance. An electrical resistance can be answered a couple different ways. How well does the wire material conduct? Copper is a great conductor. How thick is the wire? Resistance is going to be less in a thick wire. How long is it? Longer just means more resistance, obviously you have to get through more. What is the temperature? Increased movement of atoms means more resistance because there's just more interference. And superconductors are materials whose resistance becomes 0 at 0 Kelvin. Okay, some examples of what would cause less resistance and greater resistance. Here's some examples that you'll be doing in the electronics kit. These are the little tiny resistors that we'll be using. Ohm's law, symbolized by the Greek letter omega there, is the electrical resistance. So the current in a circuit is directly proportional to the voltage across that circuit and inversely proportional to resistance of the circuit. And so we get the equation current, which would be I is equal to voltage, V, over resistance, and that will be, usually is R, but it's symbolized with the Greek letter omega. So that kind of leads us to resistance isn't futile, it's voltage over current. Anyway, okay. So we can do a couple of problems with this. The resistance of a typical lamp cord is much less than an ohm, while a light bulb has about 100 ohms of resistance, because we don't want, well, we'll go into that a little bit more later. An iron or a toaster has about a resistance of about 20 ohms. So the question is, what is the resistance of a frying pan that draws 12 amps of current when connected to a 120 volt circuit? And so my current is 12 amps, voltage 120 volts. My resistance, R, will be equal to voltage over current. So 120 volts over 12 amps, I get 10 ohms of resistance. Okay, just a couple of interesting things. Maybe electric shock. That would be the current passing through your body, and depends on the applied voltage and the resistance of your body. Dry, your body could be up to 500,000 ohms. Wet, it could be as little as 100 ohms. Generally, you could resist about 100,000 ohms, and your body can do that. So if you touch the two electrodes of a battery, 12 volts probably wouldn't feel it. 24 volts could give you a little shock. Resistance of about 100,000 ohms. Here's basically the current you could be able to withstand before you'd have some problems. Let's say your feet are a little damp, your resistance is about 1,000 ohms, and you touch a 24 volt potential difference with different hands, and you're talking about 0.024 amps. So if you look back on the table, it's probably not so good. Okay, so at this point you should be able to do the resistance problems in your packet. Okay. Just as another example, if you're talking about 120 volt light fixture, you're probably going to be okay. It would hurt. If the ground is wet, it might not be so okay. Interestingly, you might see birds on electric wire, and they're okay because there's no potential. And if you were to hold on to both hands with that wire, you'd be all right. It's just that when you let go and you touch something else that has a different, you'd have that potential difference, and then you wouldn't be so okay. Okay, that third prong on a plug. Okay. Electric current, direct current, the flow of the charge in one direction only. A battery produces direct current in a circuit because the terminals of the battery always have the same sign, plus and minus. And the electrons move from the repelling negative toward the attractive positive. And even if it's unsteady, if it's one direction, it's direct current. The alternating current, the electrons move first in one direction and the opposite, and the electrons move kind of to and fro in relatively fixed position. It's not the electrons that are actually carrying the signal. I mean, they're a conduit, but they're not the ones that are traveling so fast. Generators alternate in its polarity in North America about 60 hertz. Okay, current in your home is alternating current. Batteries are usually direct current. Again, the speed of electrons in the circuit, it's the signals, the energy that's being transmitted, not the electrons. Electrons are nudged through the wire, they certainly move, but they're not the ones that are, they're not moving at the speed of light. It's the signal and the energy. Okay, going on to electric power, one of the last ones, and then I will stop and talk about circuits for the third video. Charge moves in a circuit does work. The rate at which this work is done is power, and electric power is equal to current times voltage. The standard international volts for voltage and amps for current means watts for power, and if you remember work or power when we did this with work, that was joules per second. You will find if you break down the units, it turns out to be the same. But a watt in electrical power is 1 amp times 1 volt. So if I have a lamp at 120 watts, operates on a 120 volt line, what is the current? Again, you're going to put your power, your current, your voltage. And so we're talking about 1 amp of current. Cost It is based on a kilowatt hour, and it's the energy consumed in 1 hour at the rate of 1 kilowatt. Usually it costs about 11 cents per kilowatt in the Midwest. So if you had to find out how much it cost for you to run a 100-watt light bulb for 10 hours, that would be 1 kilowatt, right? And we want to do that for 10 hours. So basically we end up with 1 kilowatt hour. And that costs 11 cents per kilowatt hour. So we're talking about 11 cents. So when your parents tell you to turn off the lights, you can say, well, it's only 11 cents. But that's only for, a 100-watt light bulb. So, okay, so you could actually calculate at 11 cents per kilowatt hour how much would it cost to run an appliance for 24 hours that draws 20 amps of current if 115 volts are impressed upon it. And so you could take your 20 amps times your 115 volts, and that would give you your power. So if we took your 20 amps of current, your 115 volts, what you're looking there as at 2,300 watts of power. And so I'll take 2.3 kilowatts. I'm going to do that for 24 hours. And I'm going to then get that answer in kilowatt hours and multiply that by 11 cents per kilowatt hour. So I don't have a calculator handy, so 2.3 times 24 times 11, and that will be how many cents it would cost you to do that. Okay, so at this point you should be able to do electrical power and the cost of electricity. So we are done for now, and then you'll have to watch the third video.